This unit on atomic physics focuses on the two modern models of the atom, the quantum or wave mechanical model of the atom, and the Bohr model of the atom. Both of these models were developed based on the observations of the interactions between light or electromagnetic radiation and matter as early as the first decade of the 1900s, and since then have been consistently supported by experimental data. Both models are used to accurately and precisely predict the chemical and physical properties and nature of matter, though the quantum mechanical model is more accurate and more precise and can be used more generally. Both of these models were based on the work of Max Planck, Albert Einstein, Werner Heisenberg, Niels Bohr, Friedrich Hund, Wolfgang Pauli, and Erwin Schrödinger. Each a genius on his own, but especially Planck and Einstein, without whom we'd probably still be back in the Dark Ages. Both models are fundamentally based on observations and measurements between the interaction of light, or electromagnetic radiation, and atoms, but specifically the electrons in those atoms, or ions or molecules, and also the production of light or electromagnetic radiation due to the relative motion of electrons, a charged particle, and protons in the nucleus of matter. Let's first focus on the contributions of Max Planck. The wave nature of light had already been established since the early 1800s, when British physicist Thomas Young, at the age of 18 in 1801, there was no internet or YouTube back then, was able to unequivocally and repeatedly show that light behaves as a wave. And he did so by passing monochromatic light through single and double slit apparati, through which he consistently and repeatedly showed an interference pattern that exists for any wavelength color of light. So that was able to establish unequivocally the wave nature of light. So that was known as classical theory, that had been established for 100 years, but there was one part of classical theory that was unexplained by the wave nature of light. In fact, the predictions of classical theory, from Young's basic wave nature premise and the Maxwell equations that describe the behavior of all electromagnetic radiation in wave form up to that point, predicted that at higher and higher temperatures, for example, when you heat up an object to the very high temperature, 3000 Kelvin versus 4000 versus 5000 Kelvin, and you observe the wavelengths of light emitted by that object, classical theory predicted that the intensity of the light at the shorter and shorter wavelengths should become infinite. That is, infinitely intense. And not only has that never been observed, but that has been completely contradicted by the observation of the light wavelength emission spectrum for any object that's heated to a high temperature. This is colloquially called, or scientifically called even, black body radiation, when a dark object such as a horseshoe or a piece of coal is heated to higher and higher temperatures. By conservation of energy, the more energy put into an object that's being absorbed by the electrons, nuclei, the atoms, the molecules, etc., eventually the more energy can be emitted, though the conservation of energy is never violated. So at higher and higher temperatures, the higher and higher the average kinetic energy of the vibrating and rotating particles, atoms, ions, molecules, the more energy can be given off. Planck noticed that even at the highest temperature that could be attained for heating an object at the time, no energy was emitted in the very, very short wavelength region, though the intensity of the shorter wavelengths increased as the object was given more energy and heated to a higher and higher temperature. So nobody before or since Planck was able to figure this out, and this was the genesis of his idea of the quantum nature of energy itself, or the quantum nature of light itself. Quantum is just a fancy Latin word for quantity or amount, and based on the empirical data from this type of experiment that led to blackbody radiation, Planck hypothesized that energy itself comes in only discrete or specific little packets or amounts, and he called each individual packet a quantum or quantity of energy. Planck then reasoned a mathematical qualitative relationship between the energy per packet or quantum and, using the wave nature of light that had already been established, the wavelength or the frequency of light that was being emitted. So to make this graph make sense to Planck and then to everybody, he reasoned that at shorter wavelengths, each packet of energy must contain a lot of energy, but at the longer wavelengths, there must be relatively little energy per packet or per quantum. How does this make sense? Well, even for the hottest object that has a lot of energy to emit or re-radiate out of the object, almost no energy was emitted at the very short wavelength region. And logically, if each little packet of energy emitted had an enormous or practically infinite amount of energy, then the object would be emitting more energy than it had absorbed, which of course is physically impossible. So you see, for all three temperatures, lowest temperature, medium, highest, in no case would the super shorter wavelength or higher frequency type of light be able to be emitted, because the energy per quantum is inversely proportional to the wavelength or directly proportional to the frequency of the light associated with those quanta, or what Einstein later called those photons. Also, at the highest temperature, there would be more energy that could be emitted or radiated from the blackbody object. So a little bit of an intensity, some of these higher energy photons or quanta could begin to be emitted without violating the law of conservation of energy, whereas at a lower temperature, there just was not enough energy to emit these higher energy photons. So, as is the case with many things in physics, the insight, the genius, breaks down to a very simple formula, and that formula for Planck was the energy of a photon is proportional to 1 over the wavelength associated with the wave nature of the light that's associated with that photon, and directly proportional to the frequency. And again, as with most equations, a constant of proportionality is empirically measured and then placed into the equation, and the proportional sign turns into an equal sign. The failure of classical theory in this one respect is known as the ultraviolet catastrophe. Maxwell's equations and the wave nature of light predicted something that was not observed and was absolutely contradicted, but this in no way, shape, or form was a failure of the wave nature of light or electromagnetic radiation. In fact, Planck had to rely on the frequency and wavelength of these electromagnetic waves in order to determine the energy of each quantum or packet. So he was the one who was able to relate the wave and particle or packet nature of light, from which all future modern atomic models rely, or came about. To determine whether there was a constant of proportionality and what that quantity was, Planck fitted the data to the black-body radiation curve and determined that for the energy per quantum divided by the frequency of a specific color or wavelength or type of light, that ratio ended up always being the same number, and the constant was later named after Planck, of course. And that is an incredibly small quantity, 6.63 times 10 to the minus 34 joule seconds. It has to have those units because the energy as measured in joules and frequency is measured in cycles per second or hertz. So for that equation to work, h, or Planck's constant, has to be joule seconds so that the seconds cancel. So generally any form of energy, but we're dealing specifically with light here, each fundamental unit of energy is a specific discrete amount or quantum, or for light a photon, and the amount of energy in that little quantum or packet or photon depends on the frequency, its wave nature, of light, and that can be mathematically calculated by Planck's equation. E equals h, Planck's constant, times f, the frequency. But we also know that for any type of wave, frequency equals the speed divided by the frequency. The wavelength equals the speed divided by the frequency. And the speed of light in a vacuum and practically in air is given the special symbol c, which is its speed. So this is also Planck's equation, showing that the longer the wavelength of light, which is in the denominator, a greater number in the denominator makes it less energy per packet, and the shorter the wavelength, the greater the energy per packet, which again is reflected in this blackbody radiation curve. The shorter the wavelength of the light or electromagnetic radiation, the more energy per packet per quantum, and as you get closer and closer to zero, or as the wavelength is closer and closer to zero, the more energy per packets, so much so that that amount of energy can't be released from the object because it doesn't have that quantity of energy. So for the past 110 years, Planck's hypothesis has been supported, verified, applied, generalized, so it's now developed into an entire theory that explains an incredible range of physical phenomena. Einstein won the Nobel Prize by designing an experiment that firmly put Planck's hypothesis on the map. And again, by unit analysis, we know in general for any type of wave, the speed of the wave, if it has a uniform wavelength, is the wavelength times the frequency. When we're talking about electromagnetic radiation, we get a symbol c for the speed of light in a vacuum, which is, to three significant figures, 3 times 3.00 times 10 to the 8th meters per second. Nothing in the universe travels faster than that speed. So we can relate the frequency to the speed over the wavelength, or the wavelength to the speed over the frequency. Plugging in the numbers for Planck's equation, since the energy per photon or quantum is Planck's constant times the speed of light divided by the wavelength, we can take these two constants, and it's certainly worthwhile to memorize not only Planck's constant of 6.63 times 10 to the minus 34 joule seconds, but Planck's constant times the speed of light, hc, is 1.989 times 10 to the minus 25 joule meters. When you divide by lambda, the wavelength in meters, you get, again, joules, the energy per photon. So again, qualitatively, Planck's equation shows the greater the frequency of light or electromagnetic radiation, the greater its energy per photon. And the lower or shorter or smaller the wavelength of light, the greater the energy per photon. Here are some general pictures of various names that we give to different wavelengths of light, from left to right in order of increasing frequency, or as you can see from the wavelengths, decreasing wavelengths. We have very long wavelength electromagnetic radiation, radio waves, TV waves, and then on the about centimeter scale microwaves, none of which is visible to humans. Then shorter wavelengths, infrared, just beyond the visual capability of people or most people. And then a tiny little region around 10 to the 14th cycles per second in frequency. And from the longest red wavelengths of 700 nanometers, 700 times 10 to the minus 9 meters, where we can detect red visible light, over to 400 nanometers. That is the little region of the vast electromagnetic scale that is detectable by a functioning retina optic nerve. Beyond the visible region, beyond the shortest visible wavelength of 400 nanometers violet light, there is ultraviolet, even shorter, and then X-rays and then gamma rays, and even beyond that there are cosmic rays. Here are some other representations, this time from shorter wavelengths to longer wavelengths, gamma rays to X-rays to ultraviolet to visible. Visible again, starting with 400 nanometer violet light, ending with 700 nanometer red light. And it follows the Roy G. Biv from longest wavelength to shortest wavelength of visible light. So that's the R for red, the O for orange, the Y for yellow, the G for green, the B for blue. Indigo is usually not included on a color wheel, but I'll put it in there for the mnemonic, and then violet. So in order of increasing visible wavelengths, that's Vib G Yor. So it is important to memorize this range in nanometers for the wavelengths, and it's also important to know that as far as electromagnetic radiation frequency, that's in the 10 to the 14 to 10 to the 15 hertz range, and that this is an extremely narrow part of the entire electromagnetic spectrum. There are other organisms that can see, literally physically see, in the invisible human region, such as the infrared. Mosquitoes can see those colors, and bees can see into the ultraviolet. This has been observed or supported by neurological, biological experiments. So colloquially, we can picture high energy light or high energy photons, as far as the wave nature, as very high frequency type of waves, and low energy per photon waves as very long wavelengths. So that's per photon or per quantum. And again, the term photon came about from the photo or light electric effect experiments of Albert Einstein. So finally, let's just look at two examples of calculating the energy per photon using Planck's equation. A violet visible photon and a red visible photon. So because violet is 400 nanometer wavelength, we'll use the wavelength form of Planck's equation, hc over lambda. hc is 1.989 times 10 to the minus 25 joule meters. Lambda is 400 nanometers. The nano is 10 to the minus 9, nano, very small. It even sounds like 9, but don't forget the negative. The 10 to the minus 25 part divided by 10 to the minus 9 gives you 10 to the minus 16, but don't forget you have about 2 divided by 400, so that puts things on the order of 10 to the minus 19. So a violet photon per individual packet of energy is 4.97 times 10 to the minus 19 joules. Keep that 10 to the minus 19 in mind, because when you have about that much energy per photon, you're probably talking about something that humans can see, visible light. For the red photons that are associated with the longer wavelength, we expect less energy per photon, and that is what we find, having a larger denominator of 700 times 10 to the minus 9 meters. The meters cancel, the 10 to the minus 9 comes from the nano, and you get 2.84 times 10 to the minus 19 joules per photon. So almost half as much energy, just as 700 is practically twice the wavelength. If we're interested in more macroscopic collections of photons, for example a mole, well, we could just take the energy per photon and multiply by a mole of photons. A mole is just a word that represents a particular number, and it's a large number. It's Avogadro's number. So the total energy of a mole of violet photons, we take the energy of one photon, 4.97 times 10 to the minus 19 joules per photon, and you could use a proportion, but why not just multiply by the number of photons, Avogadro's number of photons per mole of photons. And there you go. Joules per mole of photons. That works out to be, as you can see, 299,194 joules per mole of photons, using three significant figures and converting to kilojoules, which is the common unit for such a large number of photons. 299 kilojoules per mole of photons. For a mole of red photons, going through the same calculations, we get 170,968 joules per mole of photons, using 3 sig figs, and converting to kilojoules, 171 kilojoules of energy per mole, or Avogadro's number of photons, significantly less than the energy per mole of violet photons. And that goes to explain why you can keep a red bulb on in a photography darkroom without causing any chemical reaction that exposes the film. No single photon has sufficient energy, no single red photon does so, to cause a chemical reaction. But put even the dimmest violet bulb in a darkroom, and all of the film will be exposed via chemical reaction, because each violet photon contains almost twice the energy of a red photon, and when that photon crashes into, say, a silver atom, a chemical reaction ensues that causes the film to be exposed or developed. So in fact, Planck's theory applies to everything that we see and do, even the great art of photography.